All right, so in the past few lectures, we've talked about objects in motion that are essentially traveling in one direction, either maybe positive x to the east or negative x to the west. So this lecture, what we're going to do is essentially talk about how to set up vectors that are they still have their magnitude and direction, but instead of just demonstrating one direction, east or west, positive or negative, we're actually going to use these to demonstrate position or velocity or acceleration in multiple directions. So maybe something is going to the northeast and it has a component of sideways motion and up down like north motion. So you'll remember that there's a difference between a vector and a scalar. A scalar is essentially any measurement or any unit that doesn't have a direction associated with it. So it doesn't make sense for a mass to have some sort of direction, some sort of vector associated with it, or temperature, volume, pressure. You can have like a pressure gradient, like when a high pressure system is moving to a low pressure system, or sorry, yeah, a high pressure system is moving to a low pressure system when there's a difference between the two. But if you just have one pressure value, that doesn't have a direction associated with it. And the next semester, when we talk about charge and voltage and electronics, those things are also scalars. Now, things that do have magnitude and direction are position, displacement, velocity, acceleration. We've already talked about these. What we'll talk about next are forces, momentum, those will be coming up soon, and then electric fields. So electric fields actually have a direction associated with those as well. So we've talked about this a little bit, but it's always worth reiterating. The way you would want to represent a vector is it's essentially an arrow. Oops. And it's important to remember that the tail is placed at the point where the measurement is made. So you're not pointing to where you're making the measurement. The vector's coming away from the measurement. And it doesn't mean that that's the direction that the object is moving. We'll see shortly that you can have acceleration vectors that don't even point in the direction of the motion. Usually it's just position, your displacement vector, and your velocity. Those point in the direction of motion, but if this was a charged particle, your electric field might point in a completely different direction than the motion of the charged particle. So this vector does radiate away from the point, outward from the point which it's attached, just like these vectors here. The vector does have a magnitude and a direction. And when we describe a vector's magnitude, we always use the absolute value symbols. What that does is if the vector is pointing in a negative direction, we can use the absolute values to say we don't care about the direction. We just want that number up front. We just want the length of the vector. So you can see up here, this is our magnitude of a arbitrary velocity vector. It's 5 meters per second. And then we've got a magnitude, which is represented by length, and then we also have the direction of the vector. And for velocity, that's just the direction it's pointing in. So these other vectors here, you can see we have something we could say, oh, this might be 5 meters to the north, since it's pointing up. And this vector down here, it looks like it's almost double, maybe a little less. We could say this is maybe 8 meters to the southwest. So we get information about the magnitude and the direction. Now, when two vectors are equal, that means they have the same length and they point in the same direction, same magnitude and direction. Two different vectors, they could be at two different places on the page, but as long as they point in the same direction and have the same length, then they are considered equal. So if we look at Bill and Sam's displacements here, remember that the path doesn't matter when it comes to displacement, okay? So you can see here, Sam's actual path is actually this red line, or sorry, this is going to be red line. This dotted line, which I've drawn in red. So that was Sam's actual path. The displacement vector doesn't care how he got there. It just shows how far away he is from the origin. Now, you'll notice that over here with Sam's path and Bill's path, they're both moving to the same final displacement from their houses. But let's see, Sam took roughly this path. So Bill could have like come over here, past the point, come back down. Bill also could have took a really weird route, but because their vectors point in the same direction and are the same length, they are considered equal. Okay, and this is true regardless of where they start. So they started at two different houses, but they're still the same vector. So do keep in mind that a vector is unchanged if you move it to a different point on the page. So you can actually take vectors and slide them around if it's going to help you understand them. They don't have to be locked in right where you draw them for a problem or right where they're presented. So essentially we have Bill's vector equals Sam's vector. Now, given that we can slide things around, that's going to make vector addition really easy. So anytime we want to add multiple vectors together, well, the big vector at the end that we come out with is just called the resultant vector. We can also add these vectors to get our resultant vector any order we want. So if we have two vectors A and B, we can add A plus B plus A. Even if we had a third vector in there like plus C, we could do C plus B plus A or C plus A plus B. But for now, what we could say is if we add these two vectors together, we get a new vector, vector C, and this would be the resultant vector. So let's take a look down here at this example, and this is the graphical way to add vectors. So this is going to be us sliding them around on the page. Remember, we don't change them when we do that. But the idea here with the tip the tail method is you essentially take the two vectors you want to add together. In our case, we want to add together D and E. So we've got D here first, D plus E. So what we'll do is we'll essentially just slide E over to the end of D. And this is why it's called the tip to tail method. You put the tip of one vector onto the tail of the other. Okay, so yeah, we're essentially making a vector conga line here. Once you do that, all you have to do is connect it with your resultant vector, which is also going to come from the origin. Okay, so if this was our origin, that's where both vectors started. Our resultant vector just points to this new position. Okay, so I've drawn that out in each step, but over here in this middle panel, panel B, you can actually see that this has been done. Our resultant vector is F. We have our two components. We have D slid E over. And when we've drawn our resultant vector, which is F, there's our resultant vector. It actually comes from the origin, just like earlier. There's another way you can do it. It's called the parallelogram rule, and that's essentially where you complete the parallelogram. So you'll see the dotted lines here and here. When you complete that parallelogram, wherever you complete it at, that's going to be where your resultant vector points. But for me, the parallelogram is a little hard to see, so I like to use the tip to tail method when I'm adding graphically. Now, we can do this with a bunch of vectors. So if we had 4 different vectors, D1, D2, D3, and D4, well, if we add those up, our net displacement, remember net just means the sum, So let's put that up here. Net means, we'll say defined as sum. Okay, so our net displacement from all these displacement vectors is just, we add them all up with tip to tail. So we will start from the origin. Okay, we have our first displacement, d1. Well, that's included here. All right, well, we've got our first one. Now we need to take the tail of D and put that on the tip of, or the tail of D2 and put it on the tip of D1. Okay, now we don't know where D2 came from. Probably from right there, since it's a displacement. But remember, these vectors could have came from anywhere on the page. We're just sliding them over to add them. But I'd say in this case, since it's displacements, is probably in the right spot. Okay, so we've got D1. Whoa. Hold that thought. There we go. Okay, so we have D1. Now we're going to add D2. We can check those off. Okay, now we need to add D3. So same thing again, tip to tail. Check that. And then D4. All right, so we've got all of those added. The last thing to do is just draw that net vector. Okay, so there is our final displacement made up of those four vectors. So we just have to do it in order as they appear in the problem. We could have added D3 plus D4 plus D2 plus D1 if we wanted to. Remember, we can do this in any order. So here's a question to think about. It's going to be very similar. If we have these three vectors, A1, A2, A3, and we wanted to add these together, what would that resultant vector look like? Okay, so we have A1, we've got it already drawn here for us. Okay, A1 was easy to incorporate because it's essentially from the origin already done. Now we just need to slide A2 up there. So I'll do that now, A2. Okay, so I've added A2, I've just slid it up essentially. Okay, now I need to add A3. So now A3 is going to come down and be about right here. So notice I'm just sliding these across the page. So it looks like our resultant vector, A1 plus A2 plus A3, probably a bad idea to use an arrow to point to the vector, but right there is a net. I'll make it bold. There we go. That's after I slid all three vectors around and added them up. So it looks like C is going to be our correct answer, since when we add those up, we get the net vector just pointing down. And yep, it looks like we're good to go on that one. So in addition to adding these vectors together, you can also multiply them by a scalar. Okay, so remember, a scalar is just some number that has no direction associated with it. It's just essentially a magnitude. And we've actually been doing this. Anytime when you take one of those kinematic equations, if you have a delta x and you divide it by delta t, like for a velocity, or here where we have an acceleration, and we're taking our change in velocity divided by time, well, it turns out this is just a scalar. I can't write. Here we go. So this is just a scalar, and time doesn't have a direction, so it's just some magnitude. The 1 over delta t is just some constant, and we're essentially scaling this vector by it, this delta v. So the idea, when you multiply a vector by a scalar, you'll notice over here in the picture, we have this vector a, and essentially what happens, we have this new vector b, but b is just defined as some scalar being multiplied by a. Okay, so the question is, what happens when we do that? Well, it looks like here, when we multiply by a scalar, it stretches the vector. So clearly, this c had to be positive because we're stretching it in the same direction, in the positive direction. Looks like it also has to be greater than 1. Okay, because if c was just 1, then b would be the same thing as a. It wouldn't stretch it at all. It would just be multiplied by 1. That doesn't do anything. So clearly, since we're making it longer, c has to be a larger value. So c is at least greater than 1. We know it's positive. And that's the same thing that's happening over here with the 1 over delta t. So if we had a vector, let's say if we had a vector a, okay, and then if we multiplied it by something less than 1, so if c was less than 1 for us for some reason, then the new vector b would actually be shorter. And of course, if c was negative, it would flip the vector 180 degrees. I guess I could write that. So c is less than 0, so negative. I'm just going to leave a very quick note here. We'll say it flips vector 180 degrees. That'll be the easiest way to describe it. Now that's going to be useful for vector subtraction. So the idea here with vector subtraction is essentially it works the same way as vector addition. There's just one little difference. When you subtract, so here in this example, we have p minus q. Well, here's our two original vectors, p and q. What we have to do is we flip q 180 degrees, and then we use the tip to tail method. So we turn 180 degrees. Remember to turn the one that's being subtracted. Otherwise, you'll get not the correct answer. Okay, so we turn 180 degrees, then we use the tip to tail method. So let's take a look at this example here. So we have q and p, they're both pointed, you could imagine maybe the positive direction, positive x and positive y, but we're subtracting q, which means we have to flip it 180 degrees. Okay, and that was done here. You can see that q now points in the opposite direction. It's got to stay perfectly parallel to its original self. It's just got to be flipped. And that happened. So now we do the tip to tail method. So it's p. Okay, so this one first, p. Okay, now it's going to be plus negative q. Okay, so then we do tip to tail with negative q. And then there's our displacement, r. Okay, so r is here. I'll make it good and bold for us. So let's try this one here. So now we get to multiply by a scalar and we get to do a subtraction. So essentially, when you subtract, like when we do minus b, that's essentially just multiplying the vector by -1. That's going to flip it. So let's think about this one. Okay, so we have 2a. Okay, so we are going to multiply by a scalar. We're going to stretch this vector out, and then we're going to subtract b. Okay, so it looks like we're going to go up here this way. So here's 1a, 2a. Okay, that's my first step. 2a. Now I need to flip b 180 degrees. So it's going to point like this. So here's minus b. Okay, now my final step is just find that resultant vector, which is just going to start from the origin that we have and draw to the point where I end up. Okay, here's my resultant vector, 2a minus b, and that matches perfectly with a. So that's going to be our answer for this one, at least. So we can actually, if you'd like, we could draw in the same thing on our answer. So here we have the 2a, here we have the minus b, and you'll see that it's essentially the exact same drawing. Now let's quickly review position, velocity, acceleration, because there's some cool things here about acceleration I want to point out, but it's easier when you have vectors that you can use to talk about it with. So we've discussed position, which is just where you are at. And then if we want to talk about displacement, that's how your position has changed, right? So it's the delta, the final minus initial. That's not a rate. It doesn't have anything to do with time. It just has to do with where you're at one point and then where you move to another point. Now, if we talked about velocity, that's the rate of change. So that's your xf minus xi, but how long did it take you to do that? So that's where the delta t comes in. And you'll notice we can write this now as just essentially scaling the length of a displacement vector. So we have a displacement vector, and then we have this scalar. So that's all velocity is. It's just the scaling of your displacement and how much it needs to be scaled by based on time. Okay, so we have position, we have the rate of change of position, and then we also have the rate of change of rate of change. So where we're at, how fast that's changing, and then how fast are the changes happening, essentially. I know it gets a little confusing, but you can also, if you're very math-minded, calculus-minded, just remember that this is just your position as a function of time. Your velocity is your velocity is your first derivative, and your acceleration is your second derivative. Now let's talk about these things, position, velocity, and acceleration, in 2 dimensions. We've been talking about them in 1 a lot. So let's talk about an example over here where we consider the displacement vectors of a bicyclist dodging a large boulder. So he's pretty much driving on a trail or riding on a trail, and it's almost one-dimensional motion. We just have this little blip where he goes around a large boulder. You'll notice that we do have displacement vectors. So here, this one is essentially the final position, x2 minus x1. This one here is going to be x3 minus x2, and so on and so forth. We could go on up through here. Just remember that these are intermediate displacement vectors, not a final minus initial. All right. So we have these displacement vectors. Now, if we know the biker's velocity, we can actually scale them. So I've done that here, moving from position to velocity. So you'll notice that these new vectors I've drawn are shorter, and that just means he's got to be traveling really slow, right? The way we're scaling our displacement vector is delta t must be a big number in the denominator to make these shorter. So it could be this is a huge rock, it's taken him a long time to drive around it, and that's why these velocity vectors are smaller. All right, you'll remember from earlier in a previous lecture, the velocity always points in the direction of motion because we're just scaling that direction of motion, no big deal there. So that's worth noting. V points in the direction of motion. But now, since we have vectors and we know how to do the tip-to-tail method, we can actually talk about what's going to go on with the acceleration. All right, so if we needed to calculate the acceleration, which is just change in velocity over change in time. Okay, well, I have my velocity here, v1, and I have another velocity here, v2. So we can use these two intermediate velocities to calculate the acceleration just for this point before the rock. Okay, and you'll notice I've done that up here in this box. So I've got V2 here. Okay, my final for this intermediate step. Okay, I've got that, check. And then I need to subtract V1. Now remember, I flip it by 180 degrees. So instead of pointing up, it's pointing down. Okay, so I've included V1, or negative V1, I should say. Now I just have to draw in that resultant vector. Okay, so when I connect that initial starting point to where I end up with these vectors, that is going to be my acceleration. And you'll notice my acceleration doesn't point in the direction of motion at all. It actually points over here in the it points toward the center of this circle that I'm sort of driving around. So the path of the biker starts making this curve to the left to dodge the rock, and what's being said here is that he's accelerating to the left. His speed may be the same. He might be traveling, at 5 meters per second or whatever through this curve. So even though his speed's not changing, he's still changing direction. So that's also an acceleration. So A is a change in speed, or, this is important, direction. So that means he's accelerating into that curve. You'll notice as he goes around the rock, well, he's got to accelerate toward the rock. He's accelerating into the curve, and then when he pulls back out to get on the trail again, he accelerates back to the left, and it points in around that curve that he's traveling. So just do keep in mind that an acceleration vector does not have to point in the direction of motion. It's going to point in the direction of your change in velocity. So if you're driving in a car and you start slowing down, your acceleration vector is pointing behind you, because that's the direction that your velocity is changing. It's getting smaller. Now, everything we've done so far has just been graphically, right? We've got coordinate system, or we've got vectors floating around with no coordinate system. So now let's talk about actually sticking a coordinate system into a problem. Okay, a coordinate system is artificially imposed. That means we get to come up with the rules. We can put the origin anywhere we like. It doesn't matter. We can also rotate it if we wanted to. We could throw down a coordinate system at 45 degrees. There's no reason you can't have a coordinate system that looks like this with your x and y coordinates at a 45-degree angle. Sometimes that's actually helpful. I've noted that here, the different coordinate systems, depending on how you set them up, some may be easier in a problem than others, but the typical choice is usually just the Cartesian coordinate system, which is over here on the right with the 4 quadrants. And it's just essentially a rectangular grid. So you'll remember from, I guess, pre-calc, over here in quadrant 1, you have positive x, positive y values. Over here in quadrant 2, you have negative x because we're going to the left, but positive y values because we're still going up. Quadrant 3, negative, negative, because that's the negative x direction and the negative y direction. And then over here, we're going to have positive x values because we're again going to the right, but negative y values. So again, it's worth noting that tilted axes may be helpful for some problems. So now let's talk about actually putting these vectors into a coordinate system. And when we do that, that gives us something useful called a component vector. Okay, so if we just consider vector A over here on the right, notice it's here in bold. A, that's our regular old vector. So we can actually decompose this vector into its components. This is vector decomposition. So we can actually write vector A as the sum of two separate vectors. Okay, so you can see that here. And the idea is that AX is just the vector responsible for showing us how much of A is in the X direction. And then AY is the vector responsible for showing us how much is in the Y direction. Okay, now since AX and AY are also vectors, that means they have direction. Okay, so if AX is positive, that means the component of A is in the X direction, and if Y is positive, that means the component of A in the Y direction is also pointing up. If these are flipped, then that means we'd have A pointing maybe to the left instead of to the right, or down instead of up. So the idea here is this vector over here, AX, AX only points, it hangs out just pointing left or right. It never has an up-down component to itself. So AX shows amount, ooh, that's hard to read, but it says amount in X. And then same thing here, AY shows amount in Y. So the whole idea is you can essentially just use two simple vectors that just point left or right, up, down, add those two together to get a broader vector that has components of both. It's got some left-right movement. It's also got some up-down movement, or left-right, up-down position. Now, we could write that with like a sub x, a sub y, but what you'll see in the sciences and engineering are unit vectors. So unit vectors just have a magnitude of 1, and they have special symbols. So these are called I hat and j hat. You'll notice over here in the picture, I hat has a length of 1. Okay, so we can multiply it by whatever. It's just a length of 1. So only thing it does is it just solidifies the direction. That's why it has a length of 1. It doesn't do anything special other than just say, hey, this is my x-axis, or hey, this is my y-axis. So you'll see that I hat is over here. It lives on the x-axis. Negative I hat would be used if we wanted to go in the other direction, to the right. J hat has a length of 1 and lives right there on the y-axis, points up or down if it's negative. So the whole idea here is if we have this vector A, okay, well, we can take this vector and break it down into two simple vectors. These simple vectors are just constrained to horizontal or vertical. They don't have nice like double components like A does. We're talking about AX, AY. Those are the ones that are stuck to just the axes. Okay, but we can take those two simplistic vectors, add them together to get A. Well, AX here and AY are also vectors. So they have a magnitude and a direction. So the idea is if we just take their lengths, okay, so we're going to use absolute values. Okay, we're going to take their lengths. If we just take their lengths and then multiply by I hat and j hat, all we're doing is we're saying, okay, I hat, j hat, these are going to set our directions, our components, okay, sets the direction. Okay, so I hat, j hat, they set the direction. Then when we take, notice these aren't vectors anymore. I remove the vector hat. These are just the length values. These are just the magnitudes. So magnitudes, there's an I in there, magnitudes stretch the unit vectors. So here we're just taking these vectors with length 1, but then we're going to multiply them by scalars, and that's just going to stretch them out to the length they need to be to make up each component of our big overall A vector. Remember, all of this stuff here is just for one vector A. We're just breaking it into its pieces. And you can see what's going on graphically here. So we take I and J over here. Okay, these live there at the origin all the time. And what we do is we essentially say, well, we need to stretch I hat by some amount. So we're going to multiply it by the magnitude of A's x component. Same thing, we need A has a up-down piece, right? Because it's pointing off in a diagonal. So we multiply J by how much up and down it needs to be. You can see that AX is actually much larger than AY, so that's why AX is multiplied by more, essentially. So you can see when we're done, we can actually sum up these pieces, a stretched out I hat direction and a stretched out J hat direction. When we add those together with the tip to tail method, we actually get our original vector we're talking about, which is just vector A. And the way I like to think about these vectors is they're sort of like projections. So if you had like a flashlight here, and it was shining light onto the problem, the idea is these vectors would essentially be, these vectors would essentially be the shadows. So if you're shining a light onto vector A, so in this direction, AY, J hat would just be the shadow that's produced. If you were to shine a light down from the top, AX, AY, J hat, yes, would be the shadow. And then if we shine a light from the top, AXI hat would be the shadow as well, for essentially what's going to happen on the x-axis and what's going to happen on the y-axis. Now the question is, why do we need to make this so complicated? Why do we need to break these vectors into these individual components? And the answer is graphical addition is not useful if we have a bunch of vectors. So the idea is if we can break them into their components, we can deal with the components separately and actually do vector addition much easier. Okay, so we have this D vector here. It's just D is the net vector of A plus B plus C. Now we could take A, B, and C and slide it around on the paper and use the tip to tail method, but that requires a lot of paper, a lot of time. If we accidentally draw the wrong length on the vector or the slightly wrong direction, then we don't get the correct answer. So the idea here is we can use algebraic addition, and we don't have to worry about getting a wrong answer because we've drawn a vector off by a little bit. So essentially, let's break this down. What we're going to do is we have just the vectors A plus B plus C. Well, let's just write those out with their components. So we know A has the components AX, AY. We'll write those out here. Same thing with B. They have an X and a Y component. And C. Okay, so it's the same thing as the first line. We've just written out their X and Y components in I hat, J hat notation. But now the cool thing is, since they're all added together, we can rearrange them, okay? So if we are talking about the X piece of this net displacement vector, okay, so this is, remember, D's the answer we're gonna get, and we're talking about just the X component of D. Well, all we have to do is just take all the X pieces of all these vectors and add them together. So we just need to collect X. So you'll notice I've done that, and there's just an I hat sitting out there. So once I add all those pieces together, well, that's just my total, my dx I hat. So that's just the amount in the X direction that D is pointing is right there when I add those components up. Same thing in the Y direction. Once I collect just the Y pieces and add them up, that's going to tell me how much up or down my D vector is. So these two components of my summed vector, my resultant vector, these two components are really just determined by adding up the individual components of all the vectors involved. And here in words, it says the same thing. We can perform vector addition by adding the X component of the individual vectors to give the x component of the resultant vector. So we have the individual x components when added together become the x component of the resultant, and then the y components of the individuals give the y component of the resultant vector. And that's all that's happening here. So we can actually work backwards. We can use trig to get the components of a vector. If we're given maybe its length and an angle, because a lot of time that's actually how vectors are reported, is just with how long it is and what angle it's pointing. So you will remember your trig identities, the old SOHCAHTOA. SOHCAHTOA. So you can imagine over here if we wanted the let's see, if we wanted the y component of a vector, so let's say we wanted this. Okay, well, this is our opposite side. Okay, we want to know the length of the opposite side. We know the hypotenuse because it's given to us, because that's the original vector, it's just a. Okay, so we know our hypotenuse, which means we can rearrange this equation and just have the hypotenuse times sine of x equals the opposite side. So this is going to be the hypotenuse, magnitude of the hypotenuse, sine theta. Well, that is going to equal the opposite, because when we solve for opposite here, that's what's going to be on the right hand side. The opposite we said was ay in this case. So we'll say it gives us the magnitude of the ay vector. Now I'm going to try and change colors here. Hopefully I don't break anything. So let's say we wanted to know this length here. Let's say we wanted to know how much we need to stretch the I hat vector, the unit vector, to recreate this ax here. Okay, well that is the adjacent piece. So it looks like if we rearrange our second one here, so if we say hypotenuse, which we know is the magnitude of the original vector, times cosine of theta, it turns out, you can see that gives us the adjacent piece. So that's going to tell us how long just that projection on the x-axis will be. Now, if for whatever reason we needed to connect the opposite and adjacent pieces, so the red piece and the green piece, we also have that with our tangent, which is the opposite ay over ax. Okay, so these three will give us components. Gives components. So you'll notice we got our ax, our ay for the main vector a. Now, this bottom one, if we have our components, it will give us the magnitude. So if we know ax and ay, this bottom one, which is just the Pythagorean theorem, this is going to give us the length of the original vector. Gives length of, I think I'll call it total vector. All right, so now we can get our components and we can get our total length just from using some simple trig from pre-calc. All right, let's do one example and then we'll call it a day. All right, here I want to take A and add it to B. So I've got A down here. It's pointing at a nice 45-degree angle because it's got the same X and Y values. So we could label it if we wanted to, 45 degrees. And then vector B, notice vector B has a negative X. So this projection, so we have B, X, I hat, that's going to be negative for us. AX, I hat's going to be positive. Okay, so we want to add these two things together and write the resultant vector in terms of magnitude and direction. So we don't want an XY coordinate of where it's pointing to. We want to write this vector is this long with this angle. So we have some work to do here. So we can write this out algebraically. A is just 5 is just the I hat vector stretched by 5. Okay, you can see that here. So this is our 5 I hat. Okay, A also has 5 j hat. Now we can add those two together. 5 I hat plus 5 j hat gives us the resultant vector A. So that's just its components. Same thing here. You've got the negative 10. B also has a positive 5 j hat. Okay, we've got our components identified. Now it's time to just do the vector addition from the last few slides. So I've gathered my terms. I need to add up all the x pieces. So the x pieces are going to be 5 and negative 10 because it's pointing in the opposite direction. And the y pieces are going to be 5 and 5 again. Okay, so you can see my individual pieces here from these vectors. So I've grouped them all x's, all y's. I've assigned my I hat and j hat with them. And then when you just do the math, it's just simple arithmetic. It turns out what we get is this right here. So this negative 5i hat, and then plus 10 j hat. So if I were to mark that, so I go negative 5i hat, and then positive 10 j hat. So my resultant vector would look something like this. So this is actually A plus B. But now remember, in this situation, we don't want to report this negative 5, 10. That's how our original vectors were reported, but that's not what we want. What we want is the magnitude of this vector. Okay, so how long is it and what angle is it? Well, that's easy. So if I want the magnitude, I just plug in my new pieces. Okay, so remember I had a negative 5. So this is my new I hat direction, negative 5 I hat. And then I had also this positive 10 j hat. Well, this is my resultant vector. Here's my components. I'm just going to add them together in quadrature here, essentially use the Pythagorean theorem. And it turns out my length is 11.18. So the magnitude of my summed vector, and I'll use S as my sum, is 11.8. Now, all I need to do is just find this angle, right? So I've got one angle reported here. This is from the x-axis. It's 116.6 degrees from the x-axis. But I want this theta in here. I want it from the negative x-axis, not the positive x-axis. So look at what happens when I plug this in. When I plug in my x projection, Sx, well, Sx is negative because it's in the negative 5 I hat direction. So that means I'm essentially doing inverse tangent of negative 2. Well, I get a negative degrees here, and that doesn't make any sense. Negative degrees would be something over here because we're going the opposite direction. Remember, degrees always start counterclockwise? No, degrees go clockwise. No, degrees go this way. Yes, counterclockwise. I was right the first time. So when we have a negative degree, that means we're following the clock. So that's weird. We don't want to follow the clock. We want to get this angle over here. We want to get theta. That's marked in the picture. So this is where it's very, very tricky, very, very important to remember. You got to ask yourself, why is this negative and what angle are we talking about? Well, clearly we are talking about some angle down here, right? Because we're following the clock, we're going in the wrong direction. Now, it could be that the number 63 degrees is correct, just the wrong direction. So we have to figure out exactly what angle are we talking about here. So what I would suggest is draw this out every time. I'm going to switch colors one more time. I'm going to switch to black. Okay, so remember, the tangent is always the y component over the x component. Okay, so let's really think about this. So it's the opposite over the adjacent. Now, when we say opposite over adjacent, we have to think about what that looks like in our triangle we have here. So our opposite piece is always opposite of the angle we want. Okay, so this is across from the angle I want. I want this particular theta. Okay, so this is going to be opposite is 10. Okay, that's fine. Now, my adjacent piece is 5. The length is 5. We want to get rid of the direction because tangent doesn't care. Okay, tangent is going to give you weird stuff when you start putting in negatives. So we want to think about the absolute value. So you'll notice what happens when we plug in the absolute value related to the triangle that we want here, this angle theta, then we get our positive 63.43 degrees. And then the main punchline here is essentially, I'll write it out. So when you solve for an angle theta, when you solve for any sort of angle with these vectors, treat it as a separate problem. Pull it off the page, keep it in your head, and just think about, this is the particular angle I'm wanting to solve for. What is the opposite of this particular angle, and what is the adjacent piece of this particular angle? Okay, when you solve for angle theta, treat it as a separate problem. Otherwise, you'll get negatives in your angles and essentially get the wrong answer. Even though you have the right number, 63, you might wind up with a negative in front of it. So that's all I have for vectors. This is going to set us up very nicely to talk about two-dimensional kinematics in the next coming lectures.